Nice to all those poor souls that didn't quite recover from last night. Second rectangle. So on the left side, it controls it. I forgot to check, yes, left. And then, right there, right? Now, I always get somebody that does another one and adds in, that's 4 rectangles. You want to make sure you only use the number of rectangles they asked for and that you stay within the region they ask you to stay with. Don't just kind of get stuck on, I can draw rectangles. Here I go. So what's the area of this rectangle? 1. I love it. It's the height of 1 times the width of 1. Let me underneath this put some symbols. This is f of 1 times, let me give this guy a symbol. You ready? Delta x. This shouldn't be a surprise. Delta x is the change in x. Plus, what's the area of this next rectangle? Yeah, the height is 1/2 times the width again is 1. So this is plus f of 2 times delta x. Is everybody cool with what's happening? I want you to realize we are just getting areas of each rectangle. Will it always be pretty numbers like this? No, but who cares? Where did I get 1 from? F of 1. Where did I get 1/2 from? F of 2. So the function's freaky. You just plug the number in and get a number. What's the area of this last rectangle?
F of 3.
1/3.
1/3. 1/3 times 1.
Times 1. So that's plus f of 3 times delta x. So that equals 1 plus 1/2 plus 1/3, which is 11/6. I like it. Is everybody cool with that? Is it? Yes.
So in this case, should you be able to take the right point rectangle?
Right. So is this the right answer for the area under the blue curve?
No.
Is it too big or too small? Obviously too big. What can I do immediately to improve my estimation, still using 3 rectangles? I could find the right endpoints. Now, real quick, before I do that, well, let's do that, and then I'll be a little more precise with the symbols. Yes.
The number underneath B minus A is the number of rectangles.
Yeah, here I happen to use 1, 2, 3, 4, 5. Yeah, so the width in general is going to be B minus A over N, where N is the number of rectangles. They have to tell you a number of rectangles. Yeah. Anything from 1 to infinity. So let me see if I can do this with one more color in here. If I did right endpoints, what would the first rectangle would be this. The next one would be this. You see, now the height is based on the right endpoint. Is that cool? I mean, that's almost too nice to believe. And then here, this is this. So now the green is the right endpoint. Is that going to be an over or an under estimate?
Under.
So if I take the answer I get from what we're about to do, I average it with this, I should get a really, really decent approximation. And of course, to make it a better approximation, what could I do? I could increase the number of rectangles, increase the resolution. It's just like number of pixels. Back in my day, we had 8. So, what's the area of this first rectangle? So now it's going to be f of 2 times delta x. So it's going to be 1/2. And then f of 3 times delta x, right? Because now it's based off of this side. So this will be 1/3. And now it's finally f of 4 times delta x. And what's f of 4? 1/4. 1/2 of 1/3 plus 1/4.
It's 13 twelfths.
13 twelfths? Yeah, let's see. So it'll be 6 plus 4 plus 3. That's an underestimate. Now, if I add that to 11/6, which is also known as
22 twelfths.
good. So I get 22 twelfths plus 13 twelfths. I get, yeah, they're 20.
35.
35 twelfths. If I cut that in half, I get 35 24ths. Now, somebody help me out. What is 35 divided by 24 roughly? Let me stop. It's pretty cool with where 35 24ths came from. This is a overestimate. If I average it with this underestimate, I should get a decent thing close to the actual. Right? Do it again, sorry. 1.458, blah, blah, blah.
Yeah.
Okay. So let me show you how to do infinite rectangles on your calculator. Shit just got real. We're going to do infinite rectangle resolution on our calculator. Math is happening. I didn't bring any extra, sorry, so if you don't have what's bad, just watch. I want to show you this calculator immediately just to show you how decent this approximation is. But I just want to show you why the symbol is the way it is. Let me see if I can... All right, let's turn back around, Cal. Let me see if I can do this. All right, so here's the part. Before I do this, if I call this, for this way of doing it, I would call this x1, x2, x3. Is that cool? So for this one, it would have been x1, x2, x3. So those x sub I are the values I'm plugging in to figure out the height. Is that cool?
Yeah.
So a general rectangle's area would be f of xi times delta x. Is that? That's the number I plug in to figure out the height, times the width will be the area. And then what do I do with all the areas, each one of these? Add them. What symbol means add? You guys know? Has anybody ever seen this symbol before? Sigma. Uppercase sigma. Those of you in stats, you saw the symbol before if your teacher was worth anything. So this means, this is the Greek letter S. We chose it because we're like, what do we want to use this for sum? Let's use Greek. S. Okay. So sum these up. How many were there here? 3. Why? 3 rectangles. So I went from 1 to 3. In general, I will go from 1 to n, the number of rectangles you want. That is funky-ass notation, isn't it? But it is the most efficient way to capture the idea for anything. These are areas of rectangles. This tells you how many terms you're going to have to add. Now here's the kick-ass part. I am going to focus on this symbol next time a little bit, some math with it. But right now I want to show you, if I want infinite resolution, I would do this. Get out of there. Right? This is what I was saying earlier. If we want to have an infinite number of things, we just evaluate the limit as it goes to infinity. Can I do an infinite? No, I don't really feel like it, but I can look at the limit. here's the last piece of this. You guys stay with me now. So one option for some is to use a Greek letter S. Capital sigma. That's the Greek letter. What I love is that to capture the idea of an integral. Remember this was integration, finding the area? To capture that idea, we use a symbol that's S, but it's just an elongated S. It's like somebody wrote an S and went, oh yeah. It's like somebody tagging somewhere with a different way of writing S. So this becomes this. That's the integral. If I go to infinity, what is delta x? What's happening to the width of the rectangles if I'm going to shove an infinite number of them in here? If I put an infinite number of rectangles in, how wide will each one be? Not quite 0. dx, right? What does dx mean? Very small change in x. Unbelievably small change in x. What does delta x mean? A big step in x. And this just becomes f of x. So that is what this looks like if I let the rectangles go to infinity. So watch this. I'm turning you around. This is so cool. If you have your calculator, put the function into y equals. What was the function again? 1 over x? Okay.
1 x, yeah.
Feels like forever ago I wrote that up there. Now let's make sure we all have the same window. Let's do zoom 6 so that we all have the same window. Oh shit. That's pretty good. Now if I go second calc, because I want to calculate something now, which one of those do I want to do right now? Notice number 6, by the way. I don't know if any of you guys ever noticed number 6. It'll tell you the derivative at a point. Oh snap. Look what number 7 does though. That's what I want. And it's going to ask me from where to where. Lower limit, 1. Upper limit, 4. And look how it shades it in. Well, what does it get? 1.386. And what did we get? 1.458. So infinite rectangles, 1.386. 3 rectangles, left and right, 1.458. I'd say that's damn good. 3, infinite. We got pretty close. So that's what was either one of these by themselves close? Not really, no. But when I average them, obviously the over and the underestimate kind of average each other out, came out pretty good. Nice. Just real quick, I want to show you, just so you can really see this. Just want to make sure you really see this. This kicks so much ass. So if you do second calc 7 from 1 to 4, I mean, look at that shit. I mean, come on. You gotta love when the calculator does something. It's like, oh shit, that's exactly what I do by hand. That's exactly what I do by hand. There's the area. That kicks so much ass. We're going to talk a lot more about this. We will actually do this by hand because we are in Jeff's class and Jeff is insane. We're going to do this by hand, and then we're going to talk about how the integral connects to the antiderivative. So there will be nice, quick ways to figure it. Antiderivative, relatively simple so far. Integral, relatively simple. Even when we do this, it's, well, we'll see. And somehow the two ideas are related, which is really nice. Okay. All right. I think we can leave early. You guys need to go start corrections. Anybody not get their test back? Tim, you got one of these?
We did this side earlier. That's the side that relates to this side. That we didn't quite get to.
I think I should promise the rest of it. I have